Welcome back to the lectures in chemistry on the topic of atomic structure and chemical bonding. The topic of this lecture is the general molecular orbital method for homonuclear and heteronuclear diatomic molecules. This segment is for the homonuclear molecules, and the next one will be the heteronuclear diatomic molecules. Now, before we start, let us capture a little bit on the hydrogen molecule that we had studied so far. The wave function for the hydrogen molecule is constructed, the molecular orbital is constructed using one of the two methods, namely a molecular orbital method as a linear combination of atomic orbitals, or the molecular orbitals using the valence bond method. Both methods, when they are carried out to a very high degree of accuracy, of course, it is possible, and they both give you reasonable correlation with experimentally observed the bond energy and the potential energy graph for hydrogen molecule. The wave function in psi MO, if you recall, is a function of the positions, the radial positions R1, the coordinates R1 and R2 of the two electrons. This is a spatial wave function, SP, and this is constructed from the two one electron wave functions of the H2 plus as one possibility, namely a normalization constant times phi 1s A atom hydrogen nucleus A of R1, the electron also being in the nucleus B, the same electron coordinates. This is the wave function, the molecular orbital bonding wave function, if you remember, for the H2 plus electron. But if we have in hydrogen molecule, as we have two electrons, and we assume that the electrons are not interacting very strongly or even weakly, okay, then the two electron wave function is the product of the two one electron wave functions, and therefore, you have this phi 1s A or 2, which is the which are the coordinates for the second electron, and also distributed between the two nuclei. Okay. One of the disadvantages with such product is that if you look at it more closely and you take the products out, as you would have seen expanded, you would see that there are two types of terms, phi 1s A or 1, phi 1s B or 2, which means that electron 1 is in nucleus is associated with nucleus 1, and electron 2 is associated with nucleus 2. And since the electrons are indistinguishable, you can also have the other way around, which will lead to this particular product, namely phi s A 1s A 1 or 2, phi 1s A 1s B or 1. Okay. These are two terms of the four terms that come from this product, 1s A R1, 1s B R2, 1s B R1, 1s A R2. But then there are also two other terms, which are phi 1s A R1, phi 1s A or 2. Essentially, this corresponds to the likelihood of the two electrons being in the same atom or associated with the same nucleus, the nucleus here being A. And likewise, phi 1s B or 1, phi 1s B or 2, which is now that the two electrons are associated with the other nucleus. if you look at it carefully, all of them are weighted with the same probability, namely, sorry, this is the normalization constant. So, if we do that, we remove this whole thing with a common normalization constant, meaning that each one has the same probability. That is, the electrons being in H A and H B together, and the electrons associated with nucleus 1 leaving this ionized configuration, or H A plus H B minus, which is the other, all of them are considered to have the same probability. That is not very physical, and we believe that the electrons are more equitably distributed than having this kind of equal probabilities. Valence bond theory corrects this by introducing a small parameter, and if you write the wave function in valence bond, again spatial, valence bond theory starts with these two probabilities, that the electron 1 is associated with atom 1 and electron 2 is associated with atom 2, and of course, the interchange of the two electrons being indistinguishable gives rise to this, the other term psi 1 s A or 2, psi 1 s B or 1. Okay. Now, there is a very small probability that the two electrons may be with one atom or with the other atom. That is corrected by introducing a parameter lambda, which is extremely small, and then introducing the configurations due to these, namely psi 1 s A or 1, psi 1 s A or 2. Both the electrons are associated with atom A, plus psi 1 s B or 1, psi 1 s B or 2. Because the electron coordinates R1 and R2 both are associated with the atom B, and likewise for the atom A, but this lambda is very small. Okay. So, if you use a correcting factor like this to understand the diatomic structure, in the case of hydrogen molecule, these calculations can be done, and then you can minimize the energy of the molecular orbital by minimizing it with respect to the parameter lambda here, in addition to the other parameters that you have with respect to the wave functions. Therefore, a variational calculation can be quite extensive in the hydrogen molecule. Now, the other aspect is that this cannot be the overall molecular wave function also. The reason being, the Pauli's exclusion principle states that the overall molecular wave function associated with two fermions, or electrons in this case, must change sign when the coordinates of the electrons are interchanged or when the electrons are permuted between the two atoms. This does not. The wave function remains as the wave function if R1 and R2 are interchanged. If R1 is replaced by R2 here and R2 by R1, you see what you have here is already here, and this will, R1 and R2 interchange will give you that. Therefore, you see the wave function is the same as the wave function before or after the electron interchange. Therefore, this cannot be the molecular wave function, but Pauli's principle states that it is the overall molecular wave function, which means you have to include the spatial wave function, and let me write SPA for spatial, because the spin is also SP. Okay. Now, the product of these two should be such that if now we write psi overall R1 R2, and if we relate to this to the wave function psi overall R2 R1 obtained by interchanging the two electrons, the relation now is minus psi overall R1 R2. And that is possible if we take this linear combination That is actually possible if you do the spin wave function to be the antisymmetric part 1 by root 2 alpha 1 beta 2 minus beta 1 alpha 2. Therefore, this changes sign when the spin coordinates of 1 and 2 are interchanged, as well as the spatial coordinates of the 2 electrons interchanged. The spatial part remains the same, the spin part changes to with the minus sign, and therefore, the overall wave function changes with the minus sign. That is acceptable. On the other hand, if you have, for example, the anti-bonding case for the hydrogen molecule psi spatial SPA anti-bonding, if you write that R1 R2, one can start also with either the valence bond wave function psi 1s A R1, psi 1s B R2 minus psi 1s A R2 psi 1s B R1. Now, if you do this, you see that the spatial wave function now changes sign if we interchange the coordinates R1 and R2, because if you interchange R1 and R2 here, then this term is exactly the same as this term, but it already has a minus sign. And likewise, if you interchange the R1 and R2 here, you will get psi 1s A R1, psi 1s B R2, but it already has a minus sign, but this is positive. Therefore, the anti-bonding psi spatial is asymmetric or antisymmetric. Therefore, the psi overall, if you have to write as you did as a product of psi spatial R1 R2 psi spin 1 2, if you do that, you see that this has to be symmetric. That is, with respect to the interchange of the coordinates, the spin coordinates of the 2 electrons, this wave function should not change sign, because this already changes sign in the anti-bonding case. Therefore, you see that there are 3 possibilities for the psi SP, namely alpha 1 alpha 2, beta 1 beta 2, and 1 by root 2 alpha 1 beta 2 plus beta 1 alpha 2. Both of these, sorry, all 3 of these have an angular momentum I is equal to 1 and the projection quantum number m equal to 1 0 1 minus 1 and 0, okay, in this order, minus 1 and 0. Okay. Therefore, psi SP for an anti-bonding case should be like this. So, this is something that I have not mentioned in the earlier lectures, but it is important that when you form the n electron wave function, the fundamental requirement for the acceptability or the correctness of the molecular wave function is that the overall molecular wave function of the n electron system should be such that if any pair of electrons are interchanged, the overall wave function should become the negative of the wave function before such an interchange. So, if I have to write psi MO as the wave function due to n electrons or 2 or n and the spin coordinates 1 2 3 n, this wave function, the relation of this is it should be the negative of psi MO if I interchange, say, for example, R2 and R1. It doesn't have to be 1 and 2. It can be 1 and any other electron, or it can be any pair of electrons. An example here is 1 and 2 or 3 or n, and then you have interchanged the electron spin coordinates as well, 2 1 3, 4, etc. up to n, the relation between these two wave function is the minus sign. This is the anti-symmetry principle. Okay. This is important, and it should be with you whenever you look at the molecular wave functions for any n electron system, whether it's a molecular wave function or it's even the atomic wave function for the n electron atom, doesn't matter. It should be kept in mind. Okay. Now, let us look at the homonuclear diatomic molecule, the simple pictures that we have. In the case of hydrogen molecule, we had this nice picture HA, HB, the two 1s electrons, it is the 1s A, this is the 1s B, and the positive linear combination gave you a bonding orbital, the negative linear combination gave you the anti-bonding orbital. And in the case of hydrogen molecule, both the electrons are in the bonding orbital and paired. You see that this has been 0 state, this is a positive linear combination. Therefore, this is a stable entity, stable relative to the separated atoms HA and HB. This is of a negative energy, lower in energy. Therefore, this is a stable species. In the case of helium 2, the dimer, if you assume that the two electrons of the helium do not interact with each other, there is no electron correlation, then the helium 2 can also be extended from the hydrogen atom by writing this helium A and helium B. And you can see that if you fill this, of course, this energy gap will be different from that of the hydrogen atom, but that is not our point here. If you write this, the helium 2 will have the molecular orbitals both filled, and therefore, you see the total energy of this system is twice the stability with respect to this because of two electrons, minus the energy due to the pairing of the electrons, which is a very small quantity. That is the negative energy, but then two electrons are again in the positive energy by the same gap, therefore, no net stability. Therefore, helium 2 cannot be observed in the gas phase at normal temperatures, and this is one of the success stories of molecular orbital theory, that helium 2 dimer is not formed. I believe a few years ago there is a very beautiful experiment which suggests that helium 2 dimer is formed at extremely low temperatures in clusters, but anyway, for that we have to go into a far more detailed calculations, but this is a fairly straightforward result. The next case is, there is also a convention of labeling these atoms, okay, these energies. The label is that this is called 1 sigma G and this is called 1 sigma U. Okay. The G and U stand for Gerade and Ungerade. Which is symmetric and anti-symmetric. What it means is that if the coordinates of the two electrons are changed to a different sign, minus sign, the function, wave function becomes the minus of the wave function without the change in coordinates sign. It is not interchanging the coordinates, it is changing the sign of the coordinates, R1 to minus R1, R2 to minus R2. That is easy to see, because if you recall, the psi bonding orbital is, if you have the hydrogen atom A here and hydrogen atom B separated, you see that the overall molecular orbital is of that nature. Okay. And you can see that this whole area is positive. Therefore, the wave function, if you interchange the R1 to minus R1 or R2 to minus R2, this function does not change. On the other hand, if you have this wave function which is the wave function for the antisymmetric case, Let me just draw this carefully. Two atoms here. You see that this wave function R1, see it also takes the negative sign, and you see that the electron density also has a nodal plane. Okay. You can see that this is positive, negative, R1, R2. If you change the sign to minus R1, minus R2, this is negative, this becomes negative. Therefore, the antisymmetric linear combination is said to be of the symmetry Yun-Gerard, and the symmetric combination, which is the bonding combination, is said to be of the symmetry Gerard. This is the G and U labels that come in with that. Okay. In the case of helium 2, we still have the same thing, 1 sigma U and 1 sigma G. Helium A, helium B, this is 1 sigma G, this is 1 sigma U. This is possible only for the homonuclear atom, the homonuclear diatomic molecules, because when you interchange the coordinates of all the atoms, this is what happens. Okay. In the case of heteronuclear diatomic molecules, we do not have the G-U symmetry. The labels are simply pi, sigma, etc. Okay. So, helium 2. What about lithium 2? Lithium 2, we normally do not worry about the 1s electron because it is not the valence electron. Lithium 2, the valence electron is the 2s electron. Assuming that the 1s orbitals of the lithium as well as the bonding and anti-bonding orbitals of the lithium 2 dimer are so low in energy, these are called the core orbitals. If we consider only the valence orbital, then we write the 2s electron for the lithium 2 with 1 electron in each of the lithium atoms A, B. This is phi 2s, phi 2s, this is A and this is B. Then again a similar linear combination can be performed to give a sigma orbital and a pi orbital. Of course, the gap between these will be different from that of the 1s and so on, but I mean pictorially what you see is you have two energy levels, one which is lower than the two separated lithium atoms and another which is higher than the two separated lithium atoms. So, this is usually written by the symbol lithium 2, 2 sigma G. This is 2 sigma G and this is 2 sigma U. Okay. Therefore, the configuration for lithium helium 2 is essentially 1 sigma G2, 1 sigma U2, which is usually written as Kk. Okay. And if you write this as Kk, then this is 2 sigma G2. Beryllium 2, no problem. We have 2 electrons in the 2s orbital, phi 2s A, phi 2s B. Therefore, both the orbitals are filled with 2 electrons, 2 sigma G and 2 sigma U, and you can see that this is offering no net stability. Beryllium 2 cannot be observed, is not observed as a dimer, and you can see therefore the electronic configuration is Kk 2 sigma G 2, 2 sigma U 2. Okay. Now, boron dimer. Now, we have the 2 p electrons of the boron as well as the 2 s electrons of boron. They both participate in the bonding because they are both valence electrons as far as the boron is concerned. Now comes the difficulty, how do we define the linear combination? Should we treat the 2s electrons to form their own linear combinations and the 2p electrons to form their own linear combination? There are 3 2p orbitals. Therefore, for the 2 borons together, they will give you 6 molecular orbitals. You take 3 atomic orbitals of boron atom 1 and 3 atomic orbitals of boron atom 2. If you take the linear combination, you will get 6 molecular orbitals, of which 3 will be bonding orbitals and 3 will be anti-bonding orbitals, assuming that there is no overlap between 2s and 2p. It is justifiable sometimes to have the S and P separated, because any atom other than the hydrogen has the atomic orbitals S and P with different energies because of the electron correlation and the electron repulsion. S and P orbitals of the same principal quantum number do not have the same energy. In fact, the same principal quantum number and the S and P classification itself for a diatomic molecule with more than one electron is an approximate procedure. The sp df orbitals are exact solutions of one electron atom. They are not exact solutions of the 2 electron or 3 electron or many electron atoms. Therefore, we are already on an approximate picture. Therefore, sometimes it works that if you say the 2s is independent. So, let me write down the boron, the full electronic configuration. If you have to write the 1s A for boron atom A, and this is the boron atom B. If you do that, 1s B, this of course forms the molecular orbitals 1 sigma G, 1 sigma U. Then you have the 2s electrons forming A 2 sigma. This is 2s A, this is 2s B. This is, in the case of boron, of course, we have to continue to fill all these things. It is a 10 electron system. This is the increasing energy scale. These are deep down, these are core electrons, okay, not to be seen in most chemical bonding properties of boron. And then you have the 2p electrons, which are 3 2p electrons, and again you can see that the 2p orbitals for the boron atom are pointing in all the 3 mutually perpendicular directions. Therefore, there is a bond axis direction in which the p orbitals overlap with each other, and then there are 2 p orbitals which are perpendicular to the bond axis, and their overlap is going to be much weaker than the overlap of the 2 p orbitals which are directed along the bond. Therefore, we have a p, if we call the bond axis as the z axis, then we have a pz of the boron atom A, boron atom B, forming a strong bond, and therefore we call this as a sigma bond, because the overlap here is very strong, whereas the p orbitals which are perpendicular to the bond axis, these two are identical in nature. Therefore, they give rise to, the 2 p orbitals give rise to, for each atom, 4 pi orbitals, and these are called pi g, pi u again. Okay. Therefore, when you combine the 3 p orbitals of boron with the 3 p orbitals of boron to form a linear combination and a molecular orbital, you have a sigma g orbital and a pi g orbital, 2 of them, pi g. So, these 3 are the bonding orbitals, and then you have pi star g, which we normally call as pi, we label by 1, 2, 3 and so on. Okay. Sigma g star, the anti-bonding orbital. Let me come to that labeling next. Now, is the sigma z orbital, is it lower in energy or is it higher in energy than the pi g or pi u? I think it is very difficult to answer this question if you tacitly assume that the s orbitals and p orbitals do not interact with each other and they form linear combinations. What you see is, of course, in the case of boron, carbon and nitrogen, that the pi orbitals are lower in energy and the sigma g orbital is slightly higher in energy. This is the pi u. Okay. Now, you have 2, 4, 6, 8 and you have 2 electrons. How would you know that this is the correct answer? There are 2 unpaired electrons. Probably the magnetic properties will tell us whether this is paramagnetic or not. I believe they are paramagnetic, therefore, this is the molecular orbital structure that we have. This is the pi g, pi g, and these are labeled as 1 pi u orbitals. So, the bonding orbitals again, sorry, let me make a small change here. These are pi u orbitals, and this is the pi g orbitals. G orbitals. Okay. So, the electron configuration for boron therefore is k k for the 1s core shell, and then you have 2 sigma g 2 sigma g sigma u 2 2, that is 2 plus 2 4 plus 2 6 plus 2 8, and then you have 1 pi u 2, 10 electrons. In the case of carbon, it's again it's very easy to see. Let me fill up with a slightly different color. For carbon, if we do this, let us write that here. Carbon A, carbon B, then all you have is 2 more electrons in the pi orbital. Therefore, the carbon 2 electronic configuration turns out to be k k 2 sigma g 2 2 sigma u 2 1 pi u 4. It is a degenerate orbital. The pi u orbital is degenerate. There are 2 of them. Nitrogen, yes, immediately you can see that there are 2 more electrons for the nitrogen compared to carbon C2 dimer. Therefore, the 2 electrons occupy the sigma g, the 2p, the sigma g orbital, and the designation for this is since we already have used 1 sigma g here and we have used the 2 sigma g here, this is 2 sigma g 2 sigma u, and then this is 3, this one is 3 sigma g. Okay. Now, if you this is up to nitrogen, k k 2 sigma g 2 sigma u 2 1 pi u 4 3 sigma g 2. Okay. Now, the moment you go to oxygen, this order seems to change, this particular order. The pi and the sigma g order seems to change. The pi orbitals are slightly higher in energy, the sigma orbitals are lower in energy. I mean, these are to a certain extent, all these things are approximate. We also look at what is the corresponding molecular property, but in the case of oxygen, this is not as important as the placing the antibonding orbitals above. Therefore, if you look at this, you have this is the 1 sigma u, 1 sigma g, this is 1s, then you have 2s, you have 2 sigma g, you have the 2 sigma g here, and you have the 2 sigma u, and in the case of the 3 p orbital, the p orbitals 2p, oxygen 2 is 8 plus 8 16 electron system, and we have already 8 electrons up to 2s, and then you have the sigma z, then you have the p. With respect to the antibonding orbital, there are no problems. The pi orbitals, antibonding orbitals g star, pi g, and this is sigma u. Okay. Now, you can see this is 2. So, this is 3 sigma g, this is 3 sigma u, and since you have 1 pi u, this is 1 pi g, 1 pi g. Now you can see that the 6 electrons are in the bonding orbital, and then there are 2 electrons in the anti-bonding orbital. This is most important. Oxygen molecule is paramagnetic because of the unpaired electrons, and you can see that MO theory in an elementary form with simple linear combination gives you this particular feature, that the 2 electrons are in 2 degenerate orbitals, of course anti-bonding orbitals, but the system is net stable because you can see there is no net stability in this core. In this core there is no net stability, in this core there is no net stability, but here you have the net stability because 6 electrons are there in the bonding orbital and only 2 electrons are there in the anti-bonding orbital. In fact, there is another parameter called the bond order, which is often written for these things by saying that the bond order is the number of electrons in bonding orbital, number of electrons in bonding orbital minus the number of electrons in the anti-bonding orbital, divided by 2. It is closely associated with the number of bonds that we have. So that a single bond or a double bond or a triple bond is also directly a feature associated with the bond order. So if we say a bond order 1, it essentially means a single bond. A bond order 2 means a double bond. A bond order 1.5 obviously a fractional bond. I mean it's, so you can see that in the case of oxygen that the bond order is 2 and that there are 2 bonds, it is a double bonded system. Now fluorine, no problem, because you have to add more electrons to fluorine. So let us do fluorine, 2 more electrons, it is a 18 electron system, and the 2 electrons are added to fluorine here. And therefore, fluorine is not paramagnetic, there are no unpaired electrons, it is diamagnetic. And the last one is of course neon 2, that cannot be observed because you see that there is no net stability in the p orbitals as well as the no net stability in the 2s orbital and 1s orbital. Okay. Case of neon, that is what that is. So this is a way of filling up the molecular orbitals, but this picture is approximate. The difficulty is that the linear combination of the s and p orbitals belonging to the same shell. Even the shell structure is also an approximate structure given the fact that there are many electrons which interact with each other, and therefore there is electron-electron repulsion. The electron correlation and electron-electron repulsion is the most fundamental problem in quantum chemistry. I do not think there is an exact solution for that, but there are methods which treat them as accurately as we can using different types of basis functions. Therefore, using this idea of the s orbital and p orbitals of the hydrogen atom to give an electronic structure to either the atoms with many electrons or to simple molecular structures like diatoms and triatoms, triatomic molecules, has to be proceeded with caution. The best possible way of calculating these things is to actually use a numerical program and try using computing methods obtain the energy levels as accurately and as closely to the frequencies that we observe in the photoelectron spectroscopy of many of these diatomic molecules. And the proof of the pudding is in the eating, as they say. The proof of all these calculations is that the energy gap between the highest occupied orbital, molecular orbital, and the lowest unoccupied molecular orbital called the HOMO and the LUMO, the gap between them can actually be observed using photoelectron spectroscopy, and that is the only way by which we can correlate the electronic energy levels at this level of approximation. Okay. These are all for the homonuclear diatomic bond. In the next short module, I will also tell you a little bit about the heteronuclear diatomic molecule, where the energy levels of the two atoms are not at the same state, same energy level. The more electronegative atom has usually energy levels which are more stable, and therefore it is much lower than the energy levels of the less electronegative atoms. So, there is an imbalance in the starting point, but there is also some additional feature to that. In the next module, we will see a little bit about 2 or 3 simple heteronuclear diatomic molecules. After that, we will complete this particular course with an elementary introduction to what is called the hybridization or the linear combination that we have avoided so far between s and p orbitals of the same principal shell. When we do that, we get beautiful structures called the hybridized orbitals. We will see both of them in the next 2 modules. Until then, thank you very much.